Recording in progress.
Okay, so you might see a recording notice if you're online. I'll come where I think I can be seen. Happy New Year, everybody, and thank you very much to people both in the room and online who've turned up. I'll explain just a little bit about the cafe. First of all, for the people here in the room, if we have the fire alarm, we just need to leave. Don't stop and grab anything unless it's so close it won't slow you down. So two options: you can go down the main stairs. Don't try the lift because they do stop in fire alarm, or you can go down the back stairs over in that far corner, and that comes out at the back of the building in a little car park area. Just walk back round to the front, and we'll go over to the fences where probably the footballers are probably still playing on the artificial court right by the entrance area. Not to the building, the entrance to this whole area. So if you go back to the barrier, basically, we'll all gather there, and I'll do a quick head count to make sure we haven't forgotten anybody. If you're in the room and you need the loo and you haven't been here before, head straight across the hallway, look on the right. There's a disabled loo first, and then men's and women's straight after that. It's very easy to find. Okay? This is very informal. The cafe is not meant to be the kind of thing where everyone has to kind of pay attention without talking for an hour. So the talk will be relatively short, and then we'll take a break in the room, chance to refill glasses. I do apologise for the fact that I have no more red. I thought I had one more bottle of red in my boxes. Somehow that didn't happen. It's probably sitting on the kitchen counter somewhere. However, the red you have got, if you've been trying it, is very good. And there's some white outside staying cool if anybody would like to sample that. The other drinks, there's water in the plain jug, and in the patterned jug there is lime cordial. Ignore the notice saying water on it. I've got the wrong way around this time. Please do help yourself. Please do get up and go and get snacks and drinks if you want them at any time. So the way this works is it's short talk, quick break, and then longer discussion. If you're in the room, we'll come around to you and bring the microphone so everybody can hear, and you don't need to put comments on the suggestion slips unless you're feeling very shy, in which case please do hand it to either me or James. Give a wave. Thank you, and we will make sure one of us reads it out so you don't have to be the person with the voice being heard. But it's absolutely fine, whichever you prefer to do. Those slips are also, if you have suggestions for me of topics or very good speakers you know of, please bear in mind that I have limited funds for paying for travel. I don't pay my speakers anything, as Chris already knows, and so I do try to go for people who are relatively local, or once or twice a year I can afford somebody from further away in the UK, but no, I can't pay for them to come from Australia. That's out, I'm afraid. So it does slightly more limit who we've got coming. We will finish the whole evening at around 8:40. If you need to go then for your bus, we do understand, don't worry at all, that's fine. And we'll wrap up at the end, at which point there is a chance while we're clearing up to take a couple of minutes to grab Chris, our speaker, if you want to ask him something more private. Okay, so I'm delighted this time to introduce Chris Vogel, who started his science career studies at the University of Auckland in New Zealand, where he was a senior scholar in engineering. And then he joined Oxford for his doctorate, as the best people do, and is now a UKRI, so Royal Institution Future Leaders Fellow, focusing on fluid mechanics issues around scaling up offshore renewable energy. So there's a lot of knowledge in the area we're looking at today. Am I right in thinking you're a tutor at New College as well? And decorated for his teaching, given awards, which this university doesn't give many of, so that's impressive. So introduce Chris. I'm going to hand over to him now, and we'll see how things go.
Great. Thank you very much, and hopefully you can hear me online. So thanks very much for coming out on a cold, wet evening, and thanks for those who are joining online. As Rachel has said, my background is in offshore renewable energy, and in particular looking a lot at wind energy. So I thought I'd give a bit of a talk about that this evening, because I'm imagining it's a fairly topical area that you've got lots of questions about. I'll give just a very brief summary of some points that I think are quite interesting about how wind fits into the UK system. But there are many other things I could talk about, so please do think of lots of questions about wind turbines, wind farms, etc. And I'll do my best to give an intelligent answer. And I should say I'm part of the Department of Engineering Science, so I will take an engineering point of view of this. There's lots of other things we could talk about as well. Let's see if we can get this. Okay. Right. So I thought first some numbers, and I find this quite interesting. As Rachel mentioned, I came here to do a DPhil. I arrived in Oxford in 2011, and looking at numbers changing over the time I've been a doctoral student and eventually an academic is quite interesting. So what we've got here are the how much of the UK's electricity was produced each year from wind energy. You can see it's going up over time, as one might hope. It in general is increasing because we're building more wind turbines, but you can see there's variability year to year. Some years are windier, some years are less windy. There was this thing called COVID-19 in 2020, which meant that electricity demand was down because we're all at home. So that year, the amount of electricity provided by wind was slightly higher. But currently we're up at about 30%. You'll see the tilde on the 2025 numbers. That's because they're not finalised yet, but it's roughly 30% there. The thing that's actually quite interesting there is there's a parallel trend that's been happening over time of the total amount of electricity used in the UK dropping. In general, as we get more efficient with things, but also manufacturing, etc., moving offshore. Last year was the first time that that number has gone back up again. So although the percentage of electricity created by wind is roughly the same as in 2024, actually the total amount was bigger because the thing we're dividing by is bigger there. Lots and lots of wind turbines built on land. You've probably seen lots of them as you drive around, particularly as you go further north in the country. And I've put some numbers up here. They were updated yesterday, so these are pretty much as hot off the press as they can be. You can see a bit over 9,000 turbines and a total capacity of almost 16 gigawatts, which is a pretty large number. So that's well, I was looking at the numbers just before. Currently, the UK is generating about 40 gigawatts of electricity. It's winter, it's cold. So that's the installed capacity is quite large there. But if we divide those numbers together, 16 divided by about 9,000, each turbine is roughly 1.5 megawatts. Right? So quite big. A megawatt's a lot of electricity. But then if you look at offshore, this is where things have really been changing. And I might be a little bit nerdy, but the thing that was really exciting this year is that finally the offshore capacity is bigger than onshore. So also about 16 gigawatts, but many fewer turbines. Not quite 3,000. So the average offshore wind turbine is maybe about 5 megawatts. That is a lot bigger than the 1.5 megawatt turbine. And as I'll show you in a moment, the wind turbines that we're installing now are even bigger. And that's a really quite incredible feat of engineering. When you think about how big we're making these, I'll comment on that more in a moment. The other thing that's happening is deploying wind farms in very large wind farms, hundreds of turbines. The first wind farms are on the order of a couple of dozen turbines. What we're doing now is very big power station levels of power and hundreds of turbines. Let's advance the slides. It's not only the UK where this is happening. There is a global perspective to this. Hopefully you can see this figure okay. The big big bar, or part of the pie chart there is China, which is where most of the world's wind capacity is installed. They are building very quickly. Second is the USA. You might be slightly surprised by that, given certain trends these days, but the US does have a lot of wind and started to develop that quite a long time ago. And then lots of other countries here as well. So the UK is actually reasonably far down the list in terms of the total amount of capacity, but a lot of those countries are a lot bigger than we are. One of the things that I think is really quite amazing to think about is just how much wind turbines have changed over the last 30 or 40 years. So the picture that you see in the middle there, that is a wind farm in California, built in the mid-1980s when there was a big push to develop wind energy just post the oil crises, and the wind turbines at the time were quite small. So each of those turbines is 10, 20 meters in diameter. That photo, if I've counted correctly, has 126 wind turbines in it. And that wind turbine that you see on the bottom right is about the same capacity as those 126 wind turbines. That is a wind turbine that was installed out in the Mediterranean off the French coast. And the other thing that's incredible about that is it's gone from building wind farms on land that you can see there in California to wind turbines, that are floating. Right? So the water's really, really deep. You make them float in the ocean instead. And so those two pictures, I think, capture quite a lot of the changes that have been happening in this area over the last 30 or 40 years. That sort of 10 megawatt size turbine, that is pretty standard for what's being installed today. The diameter is probably on the order of about 150, 160 meters. And actually some of the wind turbines going in now are even bigger, 14 or 15 megawatts. So those are turbines with diameters approaching 200 meters. And yeah, they're almost as big as the Eiffel Tower. So really very, very large pieces of machinery. And what that means is these are now the largest pieces of rotating machinery we've ever built. And we're trying to install 2 or 3 of these a week from now until 2050 to meet the net zero targets. It's a pretty amazing engineering challenge. So I'm an engineer. I've allowed myself one slide with an equation on it, and I hope you'll forgive me for that. But I think it's well. There's 3 equations. That's a number. That one at the bottom is a number. So we'll just say that's fine. We're going to focus on the power equation, because I think that really captures why a turbine's changing in the way that they are. Right? So what we've got here in this equation is power is equal to half rho is the density of the air that we're looking at, and that's actually quite important when you think about changes in air density between winter and summer as the air temperature increases and decreases. We've got the wind speed cubed, and I'll make a comment on that on the next slide, but wind speed is obviously very important. A is the area that the blades sweep out. So as wind turbines get bigger and bigger, that area goes up with the square of the radius, so it's getting a lot bigger. And then finally, that term CP is something about how you've designed the turbine. And we've got this choice between, if I don't resist the flow very much, lots of air is going to go through the turbine, but I'm not doing much work on the air, so I'm not going to extract much power. So that's sort of this case on the left here. If I resist the flow too much, then actually I'm going to stop the air going through the turbine. It's just going to go around it instead. And again, I'm not going to get any power. I've got to have that air going through the turbine to extract some energy. And so somewhere between them, there's a limit, an optimal limit to the power that you would expect to get. That's this number down the bottom. You don't really need to remember that, although it's roughly just under 60%. Right? So that gives us a theoretical limit for how much of the kinetic energy in the wind you can extract. So keep these different terms in mind. It matters what the density is, the wind speed, and the size of the turbine, and then there's a bit more about the design, but we won't say too much about that now. So thinking about wind speed, this is a map of the world, as you can see. What we're looking at, and the colouring here, is the wind speed at 100 meters above the ground. Why do we look 100 meters above the ground? Well, that's the sort of side, the height where the middle of the wind turbine is. Actually, for the very biggest wind turbines, that's a bit too low. So I'll show you a few higher heights later on. And the colouring here goes from blue to sort of dark purple. Blue, the sort of darkest blue patches, it's about 2.5 meters per second average over the year wind speed. The really purple regions, such as what we've got on the North Sea, the average there is about 10 meters per second. So thinking about that equation I showed you just now, that's a change in wind speed of 4 times. Cube that up, that's 64 times more power per every unit of area of your wind turbine. Right? So this is why there are some parts of the world where wind energy is developing very quickly, because there's a lot of energy there. There are other parts of the world that there's not much wind energy. And actually, there's a few interesting patterns as to why that is. So the first thing you can see, there's a band of blue running basically across the middle of this map. That's the equator, where you get the air meeting in the north and southern hemisphere, the intertropical convergence zone. You get quite low wind speeds. It was one of the big challenges of the age of sail. How do you get across the equator? It's the same sort of problem for wind energy. The wind speeds on average are quite low here. You can see some other things as well. You can see, for example, here's the Rockies. We can see where the Alps are, the Himalayas. In general, really big things like mountains slow the wind down. The wind is accelerated through passes between the mountains, but overall the mountains are slowing the wind down. So that's not a great place to build wind turbines either. There are other parts of the world where you can see it's much redder, and that's where the wind speeds are faster. So you can see the Midwest here in America, very, very flat. So there's not really very much going on that slows the wind down. And of relevance to us in Europe, you can see particularly the offshore areas around the UK, Netherlands, Germany, Denmark, etc., are quite reddy purple colour, very high wind speeds on average. And that's because out at sea, where the sea is very, very flat, there's nothing really slowing the wind down. It can build up to really high speeds. And that's been one of the reasons for moving offshore and developing wind farms there, because there's such a good wind resource. It's also something you can see as we move away from the equator. There are large-scale atmospheric cells that result in particularly strong winds, plus or minus 40 degrees from the equator, and a few other locations. So this part of the bottom of South America, bottom of South Africa, Australia, New Zealand, also very high wind speeds, the roaring 40s. So there's a global structure to where wind speeds are strong and where they're weaker. But in the UK, we're particularly lucky that it's quite strong here. I mentioned the height having quite an important factor in terms of we need the wind speeds at the height of a turbine. This is from the same website, the Global Wind Atlas, and we're looking at the wind speeds 10 meters, 50, 100, 200 meters above the ground. If we look 10 meters above the ground, this is where most meteorological observations are taken. So you can go to the Met Office, get lots of their data. It's at 10 meters above the ground. And you can see there are parts of Scotland where it's quite red, and that's one of the reasons for building wind farms up in Scotland. The south, England, etc., you can see some blue. It's not such a good place to build wind farms from an energy perspective. As we go higher and higher, the effect of the ground on slowing the wind down is reducing, and you can see that the energy is getting larger and larger. And so that is why you want to build a tall wind turbine, because the winds are higher above the ground. And that change in wind speed with altitude is quite a complicated process. It depends also on atmospheric dynamics and so on. But it's a really important thing to consider when we think about how much energy do you expect to get from your wind farm, how tall should I build my turbines, etc. And actually, even just as one blade sweeps around, it sees a much different wind speed at the top position compared to the bottom. That's quite important for the unsteady loading that you get that ultimately determines the lifetime of the blades. Yeah. The other thing that's quite interesting, as you know, it's sometimes windy, sometimes it's not windy. This is data from a Met mast, so you can see my little cartoon of that on the right there. This is how you measure wind speed when you're building a wind farm. So you build a big tower, you take measurements for a couple of years, and you use that data to try and then predict 20, 25 years into the future, how much wind do I expect to get at my wind farm? And you might initially look at this and think this is a mess of data. But actually there are some interesting patterns that we can see. The Kentish Flats, this is, as the name would suggest, near Kent. It's one of the many wind farms that you see as you fly into London. And you can see there's a lot of data. This is where my ability to use a pointer goes wrong. And you can see quite a lot of scatter in this data. And that's because we're looking at data every 10 minutes, averaged over 2 years. There's a lot of data there. But some patterns do start to emerge. So if you look at the pointer around the year marks, you see that the wind speeds are slightly higher than in the middle. The year marks are the winter months, where we get storms, etc., coming in down from the Arctic in via the North Sea. And that's one of the things that in Northern Europe works quite well. Energy demand is higher in winter because it's dark and cold. It's also windier. And so when the energy is available from wind is when we want to use it. There's less energy in summer, but number one, energy demand is also less in summer because the UK is really driven by heating rather than cooling needs. But also in summer you get things like solar, which could replace it. So there's a nice match there in terms of when the energy is available and when demand in general is higher. So there is that seasonal pattern that you get with wind. There are variations year to year. There's no reason why it should be the same wind speed every year. And actually, you can look at very long records of wind speeds, and we do see decadal patterns in terms of oscillations going on in the North Atlantic, etc., that lead to changes in the wind speed. If we zoom in, so this little red box here is a few days of data, and you'll see there's a lot of variability even on the daily level. And that's because during the day the ground is being heated, so that's driving air flows out to sea. At night it cools down, and you reverse that pattern. So there's a day-night cycle with heating and cooling, and then there's a lot of turbulence in the atmosphere that generates quite small-scale fluctuations. So there's actually a lot of statistics in trying to understand what the wind resource looks like at a site, and then projecting that 20, 30 years into the future when you're trying to build your wind farm. One of the interesting questions is then, well, what happens when the wind doesn't blow? And this is a problem that we have already, but becoming more and more of an important problem as we rely on wind energy more. So we get these things called wind droughts, or there's a German word, kalte Dunkelflaute, which is cold, dark doldrums. When do you worry about the wind not being there? It's when it's cold, so everyone's wanting heating. It's dark, so they want the lights on, and there's no solar, and the doldrums, so there's no wind happening. And what I've plotted here is an example from early 2021, where there was about 11 days of, this blue line here is how much wind energy production there was. You can see it's almost zero across the whole country. And that's a really big problem. What do you do when there's 11 days or multiple weeks of no wind? That's the sort of thing that keeps energy planners awake at night. Now, there's an interesting thing here. So the blue line is showing you how much of the UK's, the total amount of wind that we could produce will be producing. So when it's one, all wind farms are working at 100%. This is what, on average, it would look like in the winter months for the UK. So red is high wind speeds, blue is low wind speeds. You can see a lot of black dots. These are the really big wind farms in the UK. You can see a few out there in the North Sea. So on average, our wind farms are in the right place. So where the wind is red, i.e. higher. This 2-week period is shown on the bottom here, and you can see basically all of the wind farms are in the blue region. So the wind speeds are now much lower during this period. There are certain types of atmospheric conditions which generate that. But it's not red everywhere. You can see there's still quite a lot of red. It's not blue everywhere, sorry. You can see there's still quite a lot of red up on the top of Scotland, for example, and actually also down, sorry, lost the pointer, also down here in the English Channel, it's a little bit red as well. So the point is that actually it's very unlikely to be totally still conditions everywhere across the country and the surrounding waters at the same time. Rather, there's going to be some parts where it's not windy, some parts where it is windy. So essentially, don't put all your wind farms in the same basket, spread them out, and you reduce this issue a little bit. It's still a problem of what do you do in terms of when the wind stops blowing, but it's a really important question, and how does wind fit into the rest of the system? Just a brief comment on the development of turbines. So we've talked a little bit about the resource here. I'll talk a little bit about turbines and farms, and then we'll do the questions. So wind power is not a new thing. There's been a lot of wind used for a long time for grinding grain, pumping water, etc. The oldest example I know of is from the 17th century BCE. Obviously, they weren't producing electricity back then, but it's been around for a long time. The first electricity in the UK was 1887 by James Blythe up in Scotland. The first example I'm aware of for electricity production anywhere in the world was in Vienna a few years prior to that. But obviously not much happens. The oil crises of the 70s hit, and then everyone's suddenly interested in wind because it's this free resource that they're going to develop. And there were really two schools of thought. One you've got down the bottom here is some wind turbines. It's a joint project between NASA and Boeing. You'd think Boeing, they know how to build aircraft, and so they should know how to build a wind turbine because it's just a wing that spins around. What was really interesting is that a lot of different aerospace firms which got involved in trying to develop wind energy in the 70s failed in terms of making a commercially successful project. They managed to build the devices, but they weren't a commercial success. There was a very different philosophy that started down in Denmark. This is actually quite a big example, but they decided let's build small turbines, and what the thing that we see today is basically just the I guess very big brother of what came out of the Danish wind farm wind turbines in the 1970s and 80s. So the dots here are scaled correctly with the sort of typical size of turbine from the 80s up to today. The blue dots are onshore turbines, and the green dots are offshore. You can see for a long time we do onshore. First offshore wind farm is in Denmark, early 1990s. Basically, it's just a wind turbine built for land, but put on a pile out at sea. Basically the same thing. And then it's only in the last sort of 10 years or so that offshore wind turbines have got really, really big. And you can see today these are enormous things, only possible because you can put them onto boats and take them straight out to the site where they're being developed. So here's just a few pictures. I like these because they just show quite how big they are. This is a turbine blade being built. That's the size of the factory. Basically, this is a factory size problem. Really interestingly, blades are laid up by hand. They're made out of glass fiber composites because those are very light and offer good performance. But they're so big that you build them by hand. They aren't automated, largely because, number one, building an oven big enough to cure a 100+ meter long blade is a very expensive thing to do. But also, how do you automate a process where the thickness of the skin is something on the order of tens of centimeters? There's a lot of heat generated from that process. Getting them to cure in a reliable way that you can automate is a really difficult process. So it's incredible that this thing is made by hand. They then go out to sea on large ships like this. Trying to take a 100-meter long blade on land is a really difficult prospect. And so you take them out to sea and build them up with giant offshore cranes. So it's a really incredible problem when you think about how do you put this stuff together. Turbine cost is something on the order of a couple of $1 million per megawatt. So the big turbines are obviously more expensive, but actually the cost per megawatt is pretty consistent there. One thing I'll say, so the biggest turbines being built in Europe at the moment, about 15, 16 megawatts. There are a few sort of concepts for bigger ones. The Chinese are really going for it. They've got designs for a 26 megawatt single rotor, putting two of them onto the same platform and make a 50 megawatt turbine. Just to put that in perspective, I mean, 50 megawatts is a decent sized town of power. So they're really getting quite big. Obviously, we don't build just a single turbine, we put them in farms. So here's a little example of wind farms in the North Sea. You can see a bunch of numbers there. I won't read those out, but I think what's really interesting to see is quite how big these projects are getting. So you can see that's the Hornsea 1 project in UK waters, 100 and something, 174 turbines there. Generally, they're laid out in quite a regular grid pattern, although it does depend on what the seabed conditions are in terms of exactly how you lay them out. One of the interesting problems we get, though, is what you can see in this figure down here. So this is the Horns Rev wind farm. So it's actually a Danish farm. It just happened that the weather conditions were right so that we could see these clouds developing behind the turbines. This is something called a wake. So it's a region of lower wind speed that you get behind a turbine. And you can see wake from turbine number 1 goes and hits the wake from turbine number 2, affects number 3, number 4. So predicting the energy within a wind farm is a really, really difficult problem and one of the big research questions today. So we see this sort of thing. This is some data from another wind farm. This is in Sweden. If you ever cross the Öresund bridge between Copenhagen and Malmö, this is the wind farm that you see. And there's some data of when the wind was going exactly along one of these rows. This is the sort of power you get. So the first turbine gets lots and lots of power. The second and subsequent turbines get a lot less power because of these wake effects. The coloured lines here are different engineering models to try and predict this effect, and you can see they don't do a very good job compared to the black dots. So it's quite a complicated problem. But I guess the takeaway message from all this, it's a complicated thing, and it has really significant impact on the overall performance that you get of a wind farm. So if you just took, I've got 100 wind turbines on my farm, multiply up the amount of power times a single wind turbine, actually you're getting 10-20% less than that because of these wake effects. They change all the time, which is quite complicated. Now, I'm not sure how well you can see this figure on the right, but this is, I guess, coming towards the end, just in terms of how do we try and understand what's going on these days and why is it becoming so challenging? Well, one of the things that's really interesting is that as turbines are getting bigger and bigger, they actually reach further and further up into the atmospheric boundary layer. All the important stuff for us, particularly in the North Sea, is happening within a few hundred meters of the ground. Right? And that's when your turbines were 20 meters, 50 meters, even 100 meters diameter. They were only a really small part of the bottom of the atmospheric boundary layer, so they didn't really affect what was going on too much. As they've grown bigger and bigger, they're having a bigger effect and bigger interaction with the boundary layer. The plot that you can see on the bottom left here is a simulation of a wind farm. If we don't imagine there's any temperature profile in the atmosphere, we get something like this. You can see this sort of blue region, that's the low wind speeds that we get in the wakes. That's just sort of growing with distance. Actually, what happens in the atmosphere is that it's a pretty constant temperature for a few hundred meters, and then suddenly you get a big change, and then you get into what we think of as the upper atmosphere, where the flow dynamics are quite different. And the existence of this temperature change in the atmosphere is really important. It's changing how the wind moves through this farm, therefore, if I want to predict what happens to that farm, not only do I now need to know about the wakes, which I've just shown you are quite problematic, but also now I need to understand about atmospheric physics, which is very difficult as well. And that atmospheric physics can, in certain weather conditions, create really quite long-range effects. And that's what this figure on the right is trying to show. So this is from the Copernicus satellite. It's an ESA satellite. It looks at the surface of the ground, and what you can sort of see is essentially how rough are things. So when the sea is really, really smooth, you get quite dark colours. Where it's a bit rougher, you get lighter colours. And so it's looking at reflectivity of the surface. And what you can see, I'll use the pointer, here are some wind farms. This is the German bight. You can see Denmark there, Germany here. We can see some dots for the wind farms. And then you can see these dark sort of shadows extending behind the wind farms. And they extend for tens of kilometres, sometimes up to 100 kilometres. So we talk about an individual turbine having this region of low wind speed behind it. Actually, what we can see now with these really, really big wind farms is they produce wakes as well. And they start to affect neighbouring wind farms. What's particularly interesting is when German wind farms are affecting Danish wind farm production, etc. It is a really big problem at the moment. All the Belgian wind farms, they are built right on the Belgian-Dutch border, stealing the Dutch wind in certain weather conditions. So the point of all of this is that really there's some really interesting and quite complicated interactions with the atmosphere that we see now because wind farms are so big. If we go back to the small turbines of the 1980s that I showed you at the start, this was not such a problem because they were so small compared to the atmospheric. This sort of interaction didn't matter. So just to wrap up, I'll sort of pose a few questions or challenges, I guess, that we're working out on from a research and an aerodynamic point of view, but lots of other challenges as well. So number one is scale. As I mentioned, if we're going to meet the UK's targets for building offshore wind energy up to 2050, we need to be installing 2 or 3 turbines every week, from now to 2050. How do you do that? That's a huge engineering challenge. We're trying to make the turbines bigger and bigger because, as you saw, that produces more power. So how do you do that? And the challenges of scale, as we build these bigger wind farms, they interact with the atmosphere. And so now I've got to start thinking about, well, what are the neighbouring wind farms doing, and how the atmosphere responds to that as well. Lots of uncertainty about physics that's not included in the models at the moment that we need to work on. So at the turbine scale, because the turbines are so big, the farm scales up to the wakes within the farms and the interaction with the atmosphere. And then what do you do when the wind stops blowing? Right? So that's resilience and reliability. We need to be able to predict better what's going to what power production is going to be, but also what we do when the wind stops blowing. So yeah, lots of interesting problems there. And then the final thing I'll just point to is this is from the Global Wind Council, what they expect in terms of the build out of offshore wind. We're somewhere down here at the moment, and you can see where we've got to try and get to by 2050. So it's a really big and very fast developing area. So very interesting to be involved in terms of research. Hopefully, very interesting to watch for people as well. But a really big challenge in terms of some new physics that we're seeing. So with that, I'll pause there, and I guess we can take questions and refill glasses and so on.
Thank you very much indeed, Chris, and thank you for your time, given that I started slightly late. We'll take a short break now, pause the recording, and if anybody online would like to start putting questions and comments into the chat, you're very welcome to do that anytime, and we'll read them out when we get to the discussion. Thank you, guys. Right, everybody. Oh, yeah, this is where it's going. Thank you very much, everybody, for the break, and we'll get back onto it in the discussion. So I'm going to start to see if there's anybody in the room that wants to kick off. If not, we have quite a lot of questions online. So people who turn up get first dibs. Oh, and I should have said, sorry, just 2 seconds. For people who are in the room, we use a microphone because the acoustics aren't great in here. People have different hearing capabilities. So wait until I get to you, use the microphone, and please point it directly at your mouth. If you do this, it doesn't have any. Okay, and I'll leave it switched on when I give it to you. Thank you.
As an engineer, what can you tell us about the turbine itself? What kinds of turbine are there?
Yeah, well, there's a lot of different aspects to that. So the turbines are, like, as you've seen, pretty much all three-bladed. And the reason for having three blades is because there's a balance between how much power you get for each additional blade you add, and the trade-off with the weight that you add to the whole structure. The very big wind farms and wind turbines that we're building these days, each turbine is thousands of tons. By the time you've got the generator and the cell, each blade is a few tens of tons for the really big ones. So why do they have three blades? It's that sort of trade-off between extra power versus the cost of supporting all that weight, and there are drag losses, etc. There are lots of different ways that people try to get between the problem of how quickly the turbine rotates and the speed that the generator rotates, because we want to produce electricity at 50 hertz, which means that the generator coil is spinning at 50 times every second. When you've looked at a wind turbine, I'm pretty sure you've seen it is not spinning that fast. And actually the tip speed of the blade is limited to about 100 meters per second. That's about a third of the speed of sound. And there's very good reasons why you limit it to that. Number one, the faster it moves, the louder the turbine is. So there's acoustic problems that you try to get around by limiting the speed of the turbine. But then also air becomes compressible when you spin very quickly. And so the sort of aerodynamic regime that we think about for modern aircraft, A320, etc., is very different than the aerodynamic regime of a wind turbine. Actually, a wind turbine blade is most similar to a glider plane blade. And so that limit of about 100 meters per second at the tip is related to the aerodynamics of the rotor. But what you then end up with is that the very big wind turbines that you see, they're spinning at maybe sort of 6 to 10 RPM, which is much slower than it needs to be spinning for the generator. And so then there's questions about, do you install gearboxes, or how do you essentially deal with that problem of low rotational speed for the rotor but high rotational speed for the generator? And so there's lots of different ways that people have done that. And then in terms of the rest of the structure, so it's built on a big tower. and pretty much all turbines are a single turbine on top of a single tower. There are ideas for doing something different. The tower as a cost, could we put 2 rotors on top of that? So I mentioned in passing a 50 megawatt turbine that the Chinese are building. Actually, it's got 2 rotors on a single platform. The idea being sharing the cost of the platform and so on with multiple things that generate revenue. And then how the turbine is actually supported varies quite a lot. So on land, you build it onto, you sort of put some sort of foundation into the ground. Sometimes it's just a big gravity base, so lots and lots of concrete. Sometimes you're drilling into the ground. Out at sea, most farms, and actually I've got a few sort of bonus slides. I'll find one. So one option is to float the turbines, as you can see here. So there's a few, the farm that you see on the top there, that's called Highwind up in Scotland. There's 6 floating wind turbines, and so they essentially sit on big spars, which is the type of thing that you see on the right there. But there are other ways you might design a floating platform, or you can install them directly into the ground. So this sort of structure that you see below the waterline and then into the seabed, if you can sort of visualize that in a little comic there, that's called a monopile. Almost, I think about 85% of the wind farms in Europe, offshore wind farms in Europe, use monopiles. So it's basically a big steel pile that you put into the seabed. If you think about the large wind turbines that we've got out at sea, so you've got maybe a few tens of meters, 50, 60 meters of steel below the seabed. The water depth is maybe 40 or 50 meters. So you've got over 100 meters of steel tube below the waterline. And then the tower is another 100 and something meters above the waterline. So there's a huge amount of steel, and really, really big structures involved in supporting them. There are other ways you might do it. And it really depends on what the seabed conditions are and the relative costs of steel versus labour, etc. So there's a lot of different design choices, even when the 3 blades spinning around looks the same. So I hope that answers the question.
So is there some gearing mechanism, gearbox variables?
Yes, yes.
How are you going to generate 50 hertz when you're turning at 6 or 10 or 20 or whatever?
Yes, indeed. So you've got a gearbox, and actually one of the interesting problems is looking at how do things fail and where do they fail. So the very small wind turbines initially were not didn't have a gearbox. They had didn't have a variable speed gearbox, I should say, because you just operate at 1 speed. These days it's a variable speed gearbox, which is mechanically more complicated, but there's energy benefits from being able to vary the rotational speed and the ratio with the electricity grid.
And just for those of us who've got all our physics and engineering, can I check? So the rotation of the turbine blades creates rotation in a mechanism down below, which then moves a wire, electrical wire inside a magnetic field. Is that what's going on? That's right. Yeah. So you spin the blades, that goes onto a drive shaft, maybe through a gearbox, and basically spins either a magnet or some coils, and it's that. That's right, and it's the movement of a magnet relative to a coil that creates an electrical current in the wire. Yeah. Good. So my O level, my O level physics still works.
The physics is still correct.
Good.
I'm aware that there's an optimum size for animals because animals grow heavier as they grow bigger. Their surface area, in proportion to their weight, reduces, I think. Because one's on the cube, one's on the square. There's something similar in your 2 formulae for loading and for power generation.
Yes.
Where does the balance come on those 2?
That's a very interesting question, and the answer to that has changed over time as the materials we've been talking about have changed. So the original sort of composite blades that were designed back in the 70s and 80s were really quite heavy because composites were not nearly as strong as they are today. And so what you might think of as that ratio between the weight loading and the forces acting on the blades relative to the power has changed over time. As blades as the materials get better, you can build lighter blades, and so you can go bigger. And actually, for the very large blades that we're building today, I'm an aerodynamicist. I'd love to tell you that this is all an aerodynamics problem, actually the problem of building a 100+ meter long blade is really a structural problem. Because this, as I mentioned, these are the largest pieces of rotating machinery ever built. And actually just making something strong enough so that the blade doesn't break is really hard. So the bottom part of the blade where it's attached into the nacelle is all designed around the structure and making sure this thing doesn't break and isn't too bendy. But how you've been able to do that has changed as the materials have changed. The other thing, so the square and cube relationship is very interesting. The power that you're capturing goes up with the square of the blade length, because it's a radius related quantity. The weight of the blade is going up with the cube, because both as it gets longer, you get that sort of square because you've got 3 dimensions. And so the weight is going up cubically, and that's really where the problem is, because eventually the blade gets too heavy and it just can't be supported. And so I had a picture here. You see this interesting turbine on the bottom. So this was tested in Denmark about 10 years ago now. And so the idea here was, rather than having just a single wind turbine on tower, let's share that structure across multiple wind turbines. And by having multiple rotors, I can still get that area, but with smaller blades. And so that's an idea to try and get around that relationship between the power that you're capturing being proportional to the area that it's swept out, but the weight of the blades being proportional to the radius cubed. Yes, there's lots of different ways people try to do this, but so the goalposts keep changing as materials get better as well.
Just staying on that slide for a moment, at the top, you've got water depth mattering. Presumably, there must be an issue for places which have quite high tidal variation.
Yes.
So then that reduces the amount of effective lowest water depth you can have.
Yeah, indeed. And I mean, the UK is an interesting country, that it's got the 2nd highest tidal range in the world in the Bristol Channel. Now, interestingly, most of the wind turbines that have been built out at sea have been in the North Sea, which is relatively shallow. I mean, 50 meters is still really deep, but compared to many places in the world, that is quite shallow. So that we haven't built in that sort of really tidal area. There are quite a few offshore farms in the Irish Sea where it's also quite tidal, but not as much as in the Bristol Channel. Where this is also a really big problem is, so you build them on fixed foundations up to about that depth because it's just cheaper. Eventually, when the water gets really, really deep, you'd put them on floating foundations. But you wouldn't want to do that where the depth is really changing, because it's you don't want the floater hitting the seabed at some point. It would be a bit of a problem. Yeah.
Good. If you're in the room and you want my attention, just kind of wave at me. Okay. Leave myself proper gangway through the middle this time.
Yeah, just a couple of points. How long do these generators last? I mean, and also the structure that's under the water, how long is that estimated to last? Or can it be maintained?
Yes, both interesting questions. So in general, you're designing for about 20, 25 years of lifetime. And at that point, there's a question of do you try and repurpose the structure, so replace the blades, etc., or do you decommission the entire project and take everything down? So the way that the leases work, etc., is that you're meant to take everything away at the end of that. Although we're now getting to the stage where actually there's questions about, can we essentially repower a site and say let's try and put bigger turbines on, etc. Turbines are much bigger than they were 20, 25 years ago. And so you're not going to put them in exactly the same place as you did originally. One of the issues that you have to think about, and one of the challenges, I guess, with can you just put another turbine on the original foundations? So one of the design conditions is how much does the tower rotate over time? And actually, if I go back to this picture, it summarizes it quite well. So what's pushing the wind turbine over? We've got the wind acting at the top, and that creates a big force that you have to resist with your underwater structure. But actually, even though the water is much sort of less, there's less of the turbine in the water, or the structure in the water, than there is in the air. Because water is much more dense, the forces are really high. And so I've got some sort of ranges of forces here for a typical wind turbine in the UK. And so one of the big problems is just wave loading, etc., on the structure over 20 or 25 years, particularly when you get a really big storm coming past. And so the whole thing has been designed to try and avoid rotation, and we're talking about rotation of only a few degrees. At that point, it becomes unserviceable. The turbine hasn't necessarily fallen over, but you can't insure it. You can't insure it, you can't run it. And so the design models, etc., for this have, and most offshore structures have come out of oil and gas. Oil and gas is an incredibly conservative area of engineering because the cost of failure is really high, and also they produce so much money that it doesn't matter if you've got a safety factor of 20. So over-engineer your device by 20 times. We would not be happy to pay the cost of electricity for something that's been over-engineered by 20 times. So one of the big areas of research that actually we've been doing a lot of stuff on in Oxford has been about how do you actually design this problem for offshore wind, not oil and gas. And so there's lots of work that's been going on there. Some of the design codes, etc., are very conservative, and so maybe you could reuse them. But I think the answer is we really don't know, and it's a developing area. There's also a lot of uncertainty of what's going on underground, etc. So it's a very interesting problem about can you reuse it.
Is it a specific steel?
Can you just repeat that?
Is there a specific steel that's used? I'm sure there is. I don't have that off the top of my head, I'm afraid, but I'm sure Wikipedia could help us later.
Not a metallurgist as well. How dreadful.
Yeah.
So I think we'll go to online chat. If it's been answered already, skip it. But James is going to read out one of those ones.
Yeah. So first off, is there any evidence to suggest that taking energy out of the atmosphere will have an effect on global weather?
That's a very interesting question. I haven't seen anything. I'm being very careful about this because I don't want to say no and then suddenly be wrong. I think one of the key things here is that the amount of energy that we take out is very small compared to the energy actually sort of in the atmosphere in total. And so at a global level, will it have an effect? Probably not, I think you could say. Locally, we do see changes. So I showed that image of the satellite image earlier, go back to that. And the point is here that locally there is a change in the wind speed. It's not a huge change, but there is a change. And could that potentially have an effect on the weather at the coast, etc.? Yeah, I don't think we could rule that out.
Just one point on that. If you live on the windy side of the UK, you might be quite glad if the general wind speed reduces a bit.
It might
and you're
not be a
generating
problem.
electricity.
There's a couple of questions about if the UK has enough storage capacity for the energy produced and kind of whether that's comparable to solar or other methods of production.
Yeah, so I was actually just having a chat in the break there about sort of, I guess, solar versus wind, how much capacity we're trying to build. It's a really interesting question. If you go up to 2050, it's very hard to find, we're going to build X number of gigawatts of offshore wind. You see numbers on the order of 100 gigawatts or, and the sky's the limit. And it really depends on, well, what do you think we're going to need to be generating when we go that far into the future? If we rewind 10 years, the numbers were calculated on, well, we're going to decarbonize heating, so that's going to mean lots of heat pumps. We're going to decarbonize transport, so that's going to mean lots of electrical cars. No one was talking about data centers for AI and Bitcoin, etc. Whereas people are talking about reactivating old nuclear power stations now to produce enough electricity for these things. So the target is moving, and that makes it quite hard to evaluate. But all the scenarios that I've seen always have more wind than solar for the UK. It's a windier country than it is a sunny country. But exactly what that balance is depends quite a lot on what you say the costs are going to be for solar, what are they going to be for wind, what's the cost of storage, is it cheaper to overbuild and just say we're going to deliberately waste some of the electricity rather than try and store it because the storage is expensive, The thing I mentioned wind droughts there briefly. Every year there are periods of a week or so where there's basically no wind generation. A week you can sort of imagine. Every so often though, it's not impossible that there might be a month of no wind production, and the amount of extra storage that you need to go from a week to a month is enormous. So what you do about the worst, well, what you define as the worst case and what you do about it really does drive that question. So it's not really an answer, but it's just it's hard if you want to fund research, and it would be a great idea.
One point though is I remember, was it 22 when we had that really hot August? So that was when we had very little wind, but it was huge solar generation.
Yes,
so
and actually that's one of the interesting things. So high pressure weather systems that bring us wonderful weather in summer, it's very, very still. And so that's why we don't get much wind, but it also means there's a lot of solar. And so a high pressure system in summer is not a problem. A high pressure system in winter is a really big problem because again, it's not windy, but there's not much sun.
Hi there. You haven't mentioned much. Sorry. Economics. You've got loads of variables with the atmosphere and the waves, etc. How dependent is the return on investment on energy price?
That's an interesting question. So the way that that wind is, or renewables in general, are funded at the moment in the UK is there's a bunch of allocation rounds, which are essentially auctions where the government says, you know, we'd like to contract capacity to be built in X number of years' time. What's the price that you'll accept? And so that's not really competing on the open market in the same way as purely natural gas or something like that would be running. And essentially the reason why we do it that way is because most of the cost of building a wind farm is incurred before you start production. So it's something on the order of 80% is incurred before the farm switches on. The remaining 20% of cost is over the rest of the lifetime. For a fossil fuel generation system, natural gas or something like that, it's pretty much the opposite ratio. Most of the cost is actually the fuel that you're burning rather than the cost of the plant. So having that cost or financing structure up front has been really important for enabling this technology and other technologies to develop. In the UK, the costs have come down, and there's a lot of debates about what the actual costs are versus the prices that are guaranteed. But we can talk about the prices guaranteed because that's stuff that we can actually see. The way that mechanism works is if the wholesale price of electricity is below, the government, via our bills, tops it up to the guaranteed price. If it's above, then the companies return the extra funding. So it's quite a hard question to answer about cost because the way that it's funded is not entirely related to the instantaneous price of electricity. I could find the numbers, I don't have them to hand, in terms of what the cost of the subsidy to wind and solar, etc., has been. But it's not always that we're paying from taxes or our bills to it. When Russia invaded Ukraine, natural gas went through the roof, so the wholesale price of electricity was very high, and it returned hundreds of millions of pounds each month to the well, I guess Treasury ultimately, because the price was much higher than the guarantees. So it really depends, I guess, on what you think the future is going to be relative to the prices that have been agreed.
Yeah. The thing that I'm looking at in the future is if we're going to get towards net zero, we won't have any fossil fuel generation. And so the energy price based on fossil fuel generators will not exist.
Yes.
And it doesn't cost anything to get electricity from the wind other than the cost of you putting up your wind bill and how long it survives to pay you back. So how do you factor that into the build in 2050?
It's a very interesting question, and it's something that I don't think we've got an answer to. Well, we don't have an answer to at the moment. We're still using the system based on essentially the price of natural gas. But it's something we need to do something about, because as you say, as you get less and less fossil fuels in the system, actually the marginal price becomes higher because you're running at less of the time. But that's not a good way to price the whole system. It does introduce interesting dynamics because it's free, the wind is free, and so you might as well sell the electricity. And that's why we sometimes get negative prices these days, because essentially, I don't want to switch my wind farm off, so I'll pay you to take the electricity. I don't want to turn my nuclear power station down because that's a really hard thing to do, so I'll pay you to take the electricity, etc. So we see much more variability in prices because of this dynamic of not wanting to switch off, and essentially we've committed to pay the cost of the electricity. The other thing maybe to mention here is the ability to get the electricity from the wind farms to where the demand is. One of the big problems in the UK at the moment is there's a lot of wind up in Scotland. Demand is down in the south, and unless you can transmit the electricity, you again run into this problem of we're paying for electricity that we can't use. And National Grid are doing some very big upgrade work at the moment on the transmission, but it does mean that some of the wind farms up in Scotland are being shut down when they could be producing, and there is still demand for the electricity just because it can't be moved to where it's needed. So yeah, this is a problem that we need to think about at a system level to how do you fund the whole thing.
Okay, I'm going to go here in the room, and then we'll do one online if James can pick out a good one, and we'll go back to the room again and get some other people.
Yeah, just one query actually regarding batteries and all this. Are we building huge battery farms?
Yes, the UK has some. Again, I don't have the number just at the top of my head, but it's got a huge capacity of batteries installed across the country, because I guess it makes a lot of sense that there are times where the price is very high, so it'd be a great time to sell electricity. There are times of the day where electricity is very cheap, so it makes a lot of sense.
And finally, I mean, I don't know if you know, how long does the battery charge hold in these batteries?
That's the key question, actually. So batteries are good. They make economic sense and technical sense if you're talking about trying to store energy on the order of a day. So, charging within, for a few hours, discharging a day, a few days type thing, they're not the technology that you would want for seasonal storage, charging in winter and waiting until summer. So on the energy storage side, we need a whole suite of different technologies targeting different periods that you want to store the energy for.
So things involving gravity and moving weights up and down are much more effective for that kind of long-term storage.
Yes, well, there's a great idea. Pump water up a hill, run it down again. The pump storage. Sorry? Are there enough hills? No, the UK is a relatively flat country. So there are a few of these pump storage stations in the UK, but there isn't the capacity to build enough more to solve our energy storage problems.
More than the Dutch have, though.
More than the Dutch.
Okay,
yes.
we'll do an online.
So there's a lot of kind of difficulties with wind turbines in high winds, and them often being told to shut down because there are problems. Are there any technical developments currently being addressed or looked into to see if we can help and harness these strong winds? Yeah.
So it's really a trade-off between number one, is it safe to run in high wind speeds? And that's a design question. And then what is the cost of designing your turbine to do so? So for the UK, most of the wind turbines that we have, they would shut down at wind speeds on the order of 25 to 30 meters per second, which is really, really high wind speed. Something on the order of 100 kilometers per hour. Someone with a calculator can do that calculation properly. But essentially, the really, really strong winter storms that we get may be shut down, but they should survive most of those. There is a question. So sometimes it's about shutting the turbine down for safety. The blades bend under wind loading, and one of the reasons why you shut the turbine down is because you don't want the blade to hit the tower, because that's something that happens only once in the lifetime of the wind turbine. So that's a reason for shutting down. There are parts of the world where the extreme wind speeds are much higher. So China and Southeast Asia in general with typhoons, the wind speeds there get up to 70 or 80 meters per second that you're trying to survive. So you shut down those conditions because it's so energetic, trying to control the turbine and make sure it's operating safely in a way that you can still use it tomorrow. It's not worth running. So the really extreme wind speeds you might shut down to protect the turbine, because the cost of making it strong enough would mean we wouldn't be happy to pay for that price. But the other part is actually sometimes you might be producing all the power you could possibly take. The total wind capacity in the UK, 32 gigawatts. Well, actually today we're using something on the order of, I think, about 38 to 40 gigawatts. So if it was really windy across the entire country, then actually we could produce almost all of the electricity we need from just wind. But we want to keep the nuclear running because you don't want to be switching nuclear on and off, and other things have to keep running. So actually, you can't take all that electricity. If it's really windy here, it's probably really windy in the Netherlands, and Belgium, etc. They're trying to get rid of their electricity as well. So actually, you shut down because you can't take it again because we don't have storage solved. So there might be multiple reasons for shutting down, and again, you can't transmit it to where it's needed, etc., etc. So yeah, it's not only because of surviving that you might not operate.
Okay, let's go in the room. So you go first.
In terms of storage, again, if you build a huge water reservoir up in the mountains, you've got it sitting there waiting for you to run down through it.
Yes, yeah, so that's essentially what things like De Norweg pump storage are doing. There's an interesting question. So De Norweg often runs on a daily basis. It provides extra power when there's high demand in the morning and in the evening, and then you charge it up when the price is lower. If you were to try and do pump storage over a really long period, so let's say seasonal type stuff, you then have to start worrying about you pump this water up and now it's evaporating from the top, or it's freezing over, or something like that. So again, it's not necessarily the best solution for really long-term stuff, but better than batteries. And actually, maybe one of the things that so there's a lot of interconnectors between the UK and other countries. One thing you could do in Norway is just they don't run their hydropower, sell them wind power when it's really cheap here, and then when there's no wind here, use Norwegian hydro. You don't actually need to worry about pumping up the hills because the rain and snow, etc., has done that for you. Yeah, lots of ways to do it.
A couple of questions. Yeah. Given the very high tip speeds of the rotors, is there a common erosion there?
Yes. So I'm not sure whether I've got a photo of that in my sort of bonus slide. So the question was about erosion on the ends of the blades. I don't have a good picture. There are some really interesting photos you can see online of this. So we've got this blade traveling around close to 100 meters per second, hitting dust or even rain droplets in the atmosphere. There's a very high impact speed there, and over time, the leading edge of the blade does erode. And there are some fantastic pictures you can see online of people abseiling down these blades. The person sort of applying a sort of protective film looks absolutely tiny compared to the blade, because that's just how big these things are. But yes, repairing the front edge of the blade is a really challenging process, and it's a really important thing to do, because over time, as that erosion happens, the aerodynamic performance of the turbine reduces. Knowing that it's happened is also a really hard thing to do when the turbine's way out at sea and you can't see it. But that's a really important problem. The other thing that can happen, actually more temporary, is ice forming on the blades. This is pilot friend over there. Why do you de-ice your aircraft before takeoff? You want a really smooth surface for good aerodynamics of the aircraft. Same thing for the wind turbine. In winter, ice will form on the blades, and that disrupts the airflow over the surface, so it's not going to perform as well. One of the problems that you then get is that ice gets thrown off the blade at some point, and so then you've got these car-sized chunks of ice flying around the wind turbine. So it is a safety problem. What do you do about the ice, which has a similar problem? At least it's a temporary problem.
second question, what's the impact on bird life?
Yeah, that's an interesting one. So I think, you know, I'm not going to be one of these people who says there's no impact. Particularly really big wind turbines, very high speeds. A bird just won't see that there is a blade there, and so you hit birds. Many more birds are killed by cats than wind turbines. So you've got to put it in perspective, but it is a problem. So what are people doing about it? There's been discussions about it. So one of the problems is all the blades are white, so the birds don't see that because it's designed to blend them because we don't like looking at wind turbines. If you had different colour blades, then it would be more obvious. So maybe they'd fly away or avoid the turbines. Sometimes wind turbines are shut down because of migration patterns, and so particularly, I guess, offshore you get migrating birds, and so there are periods of the year where you shut down the wind farm because of migration to avoid any impacts. And then more recently, there's been work on trying to develop systems to deter birds or detect the presence of birds, and then again you would shut down to protect bird life. So using lasers and sort of AI recognition, etc., to see, you know, is this a bird? Is it likely to be in danger? Do you shut the turbine down or do something to try and protect it? So definitely a problem, but there is also some quite interesting work going on to try and mitigate that problem.
Got loads of questions online. I've come up with an idea rather than try on our speaker in a minute when we finish, but to try and solve that.
Just a quickie. I can see the attractions of draftsmen of laying out a wind farm on a regular grid pattern, but soldiers break step when they cross bridges. Shouldn't they be set out at random to avoid this shadowing effect?
Yes, well, it is a very interesting problem, and sometimes, I mean, if we go back to the picture with the wakes, so I mean, this is a particularly it's a fantastic photo, see the wake effect. But if the wind were to change by just a few degrees, suddenly this wake from the first turbine that hits the second turbine would totally miss the next one. And so what we do is, when you're building your wind farm, you look at both what the wind speeds are, but also what directions are most likely for the wind to come from. And you don't want to align your turbines exactly in the most common direction. There are also things you can do to try and deflect where this wake from the first turbine goes onto the second turbine. So if I turn the turbine slightly, so it's angled slightly away from the wind, then the wake is going to go out and maybe miss the next turbine. So there's some interesting farm level type control things you might do to try and reduce the impact of this. But it's, you know, this is where a lot of the research needs to happen to understand, well, how do these wakes evolve and what's the effect of the atmosphere on their evolution, etc.
And any chance that the floating platform turbines are able to rotate?
Yes, so they go back to a picture of a floating turbine. So the top of this structure is going to yaw around, but the whole floating platform will just naturally move a bit in the waves, etc. There aren't many floating wind farms. It's a very new, still quite an expensive technology. About 80% of the wind resource that you might try and exploit globally is in water where you have to use floating platforms just because of how deep it is. So it's a big thing that presumably has to happen. Now, these are going to move around a little bit, so trying to predict now where the wake is going and therefore how you're going to control it, etc., becomes even more difficult. So yeah, it's something that we're doing some research on at the moment.
Very good for people with fluid and aerodynamics knowledge. We'll do one more online. This is probably going to have to be the last.
So you've spoken a lot about the wind aspect of it. Are there sort of similarities with the wind power and tidal power? And
it's an excellent question, and something I could speak for many, many more hours on. The other big part of research that we do is tidal power. So for those who aren't familiar, tidal energy is, there's two different types. One, you can use the difference in height of the water, and that's called tidal barrage technology. And then there's tidal stream, which uses the fact that you're moving huge amounts of water with the tides, And so using the speed there to try and spin some blades, and they look a lot like wind turbines, but underwater. I'm doing a bit of an injustice to the technology, but you could think of it like that. Why would you do that? Well, if we go back to the power equation, so you can't build such a big tidal turbine as a wind turbine because the water is just not that deep. But the important part of the equation is the rho there, the density term. Water is about 800 times more dense than air, so there's a lot of energy in water, even if it moves a bit more slowly and a bit less quickly. Sorry, a bit more slowly and a bit smaller turbines than air. So definitely some interesting potential there. There aren't as many countries in the world where tidal stream or tidal range either would have such a big contribution as wind. So for the UK, it's very hard to estimate how much the resource is, but it could present something on the order of 10% of the energy demand for the country. If you were to build out everything, is that economic is a different question. But the reason you might consider it is because unlike wind, which sometimes it blows, sometimes it doesn't, it's a chaotic system, so very difficult to predict. The tides are generated by gravitational interaction between the sun, the earth, and the moon. And if we don't have the sun, the earth, and the moon, then we've got bigger problems than climate change. So there's a slightly pithy comment. The predictability is the real attraction there. So it's a developing technology. There's some sort of initial farms and so on being built, but it's never going to be as big as wind because the resource isn't as large globally.
I'm going to have to bring things to a close. A couple of things. So we have quite a lot of comments as well as questions online. So I think what I'm going to do is publish that chat to the mailing list straight away. So I think people in the room would find it quite interesting to be able to read some of the comments other people have made on the chat. And obviously, Chris, if you want to take a look, you can. But also, I'm going to ask James, who's helping me tonight, to go with you down to the next level. It's quieter while I'm clearing up. And if you would just go through with him, I'll keep the recording on. If you would go through with him what some of the questions and answers are, that would be really helpful. I think that would work very well. Then we can get onto the recording, some of the extra questions on the chat. There are some that have been answered, there are some which mirror things in the room, and there are some comments, but I think there's 2 or 3 more there, which would be worth covering.
Yeah.
Fantastic. Before I thank Chris tonight, thank you obviously to everybody who's turned up and everyone who's come online, fantastic. To the Department of Pharmacology for giving us the space for free, which is very nice of them. To anybody who's donated, we have the black hat in the room. We also can take donations through the website at the bottom of the front page if you want to have a look there. If you haven't joined the mailing list but just came across this, then you can easily Google Oxford Café Scientifique and you'll find the website there and you can put all the information about it. Looking ahead, we have next month. So I know the people who love stuff about medical issues and the human body are going to hate this, but we are going to stay with the physical sciences for a while because, you know, it's their turn. And also, it just happens it's that time of year when people are interested in talking. We have Zoe Tinacci, who's from a company called Astroscale. What they work on is the engineering problems and the practical problems of trying to remove space debris, including self-running automated units that will go around collecting bits of space debris out of the upper beyond the atmosphere. So that could be another quite important one with kind of impact for the Earth, and she'll talk about that. That's on, I think it's the 10th of February, so Tuesday the 10th of February. And then in March, 10th of March, we've got The Thirsty Earth, all about droughts and how that affects human populations, animal populations, etc. And we can do about it. After that, things aren't quite fixed, but we'll fill in the blanks as we get there. Do look at the website. There's a menu on there that says dates. If you look there, you can see everything ahead. But actually, I've got the dates for the rest of this academic year on the front page as well. So fantastic. But the biggest thanks of all to Chris tonight. I can absolutely see why he's a great teacher, not just the engineering, but also the general explaining and putting an answer together. Spot on. Very, very good. Thank you very much indeed. It's been a great evening.
If I turn this If I do one, ooh, that's gone horribly wrong. If I do that. Okay, I think that should work. Fab, so this is just working through the questions in the chat. Speaking about that, is there any evidence for the effect of offshore installations on sea currents, sandbank drift, etc.?
Yes, so one of the problems that you can get in wind farms, particularly if you're installing them in really sandy locations, is you've put these big structures, the monopiles can be multiple meters, up to 10 meters in diameter. That affects how the sea currents move over the sand, and then you get this process called scour, which basically slowly the sand erodes away from near the base of the turbine. And that's a problem, because if you remove the amount of material that was sort of helping keep the pile and the tower in place, then eventually the turbine will rotate more than you expect it to. So it does happen. How much it happens really depends on the particular location where you've installed the farm.
We've slightly touched on this, but to kind of get a solid answer on it, does the UK have enough storage capacity so surplus electricity generated is not wasted?
Well, enough is an interesting question. At the moment, we do not have enough capacity to store all the electricity we might generate if we were to do 100% wind and then reuse it in summer when there's less wind, etc. It's really a mix of having both storage capacity with a range of different storage options for short-term, medium-term, long-term storage, but then also connections to other countries. So sometimes it might be really windy in the UK, and so we can send that electricity over to other parts of the world, say France, Germany, etc., where there are interconnectors, and they can use it there, and vice versa. So it's a mix, I think, of both the storage and the transmission capacity that is needed. But if we think about what we will need in 2050, we're a long way from that, and in particular on the longer term technologies.
Can you talk about the life cycle of an offshore wind turbine? Will it last forever? Does it need maintenance monitoring? And how do they fail?
Yeah, very good question. So the life cycle, you build your blades in a factory. They're made out of some sort of composite. There's lots of steel in the support structure, both below the seabed, through the water column and up to the top of the tower. The generator, etc., is also lots of metal components, and depending on the type of generator you'll have different sorts of rare earth metals there. During operation, yes, absolutely, maintenance is needed, and I believe the number for the UK is that they're offshore wind turbines are inspected 13 or 14 times a year, and that's a sort of preventative type approach to monitor how things are going. The components that fail first have really changed over time, also with the different sizes of turbines. So I guess it's preventative maintenance with increasing amounts of data that you can gather with embedded sensors, etc. You can also monitor frequencies in terms of the generator temperatures in the system, and that helps you identify do you need to do some sort of preventative maintenance as well. So there's a lot of work there trying to make it more automated and therefore cheaper. And then eventually you get to the end of the lifetime, and there's a question of, well, what can you recycle? At the moment, a lot of the turbine, the metal bits can be recycled because it's steel, etc., and that's fine. What's more challenging is things like composites. They are very hard to recycle, and a lot of blades do go into landfill, although other uses are being proposed, crushing the composite materials and reusing them in different aggregates and so on. I even saw something a couple of years ago now saying that you could recycle with a slightly different resin and basically with the same sort of stuff that's in jelly babies. So there's all sorts of ideas. There is quite a lot of work going on to make properly recyclable blades, and rather than using thermoset resins, which release a lot of heat when they cure, and are very difficult to recycle, instead using what's called a thermoplastic, which cures in a slightly different way. I'm not an expert in that area, but the idea of thermoplastics is that you would then be able to recycle the blades and reuse that material in making new blades or other applications.
Is there a difference in maintenance intervals for gearbox versus kind of non-gearbox turbines?
Yes, yeah, and over time, I mean, this has been one of the things that, starting out from the beginning of wind turbines, the difference in philosophy between very large and quite mechanically complicated turbines that the aerospace manufacturers were building versus the very rugged and simple turbines that the Danes developed initially. Those initial turbines, they were designed so that the speed was controlled by the connection to the electricity grid, so you didn't need to have complicated machinery there. The blades always operated at one particular fixed angle, so you didn't need complicated machinery there. But sacrificing that mechanical complexity does mean that the energy efficiency is lower. And so as turbines have got bigger and the imperative to design them to be really aerodynamically efficient has increased, we introduce things like speed control and blade pitch control, etc. These are extra areas which fail, but the point is that actually you can balance that off and the cost of doing maintenance with the increased energy that you capture with a more efficient turbine. Yes, there are extra failures that you get, and one of the big areas of work over time has been trying to drive those failures down.
On one of the slides, it looks like the efficiency of wind farms drops to 40% from a nominal 100. Is that right? And what's the main reason we don't space them out further?
Yeah. So I think that may have been in. If we can just get to the slide. Click on that, maybe. Just try and get to the slide on the screen. So I think this is the slide I think this question is in reference to. So what you see in that plot on the bottom left, it's GB, Great Britain, and we're looking at Great Britain here because the island of Ireland is on a separate electricity network. So Northern Ireland and Republic of Ireland are separate. So we're looking at just GB wind farms, and the CF, that's an acronym for capacity factor. What that means is it's how much power have you produced relative to if everything was operating at 100%. It's not really the best metric for looking at variable renewable technologies like wind and solar, but there's a long history of using this particular metric in the energy sector, so that's why we use it. But you can essentially look at this as the ratio compared to if every wind turbine was operating at 100%, how much power are you actually generating at that time? So the long-term average, you can see there indicated with the red line, is just under 40%. And that's looking at this data and imagining if you had sort of 40 or 50 years of these wind farms running, what would you have expected to get? That value varies depending whether you're onshore or offshore. So onshore, where wind speeds tend to be a bit lower, the capacity factor is lower. Offshore, the number is a bit higher. Something on the order of 36 to 40%, I think, for offshore wind farms. It varies a bit year to year, depending on how windy it's been. The number really varies, and it's basically saying how much wind did you actually get over time.
We're going to have to stop there. Thank you so much, Chris. That's really kind. Stop recording.
Right, thanks for the questions, everyone.
Stop recording.
Perfect.